Hi, welcome back. In this lecture, I want to talk about reversible quantum arithmetics operation, and I will explain a simple technique based on the so-called scratch qubits. And we are going to take an example, the absolute value function, and we're going to make it reversible using the scratch qubits. So we know that a QPU operation and quantum gates operation must be reversible because the quantum physics laws are reversible. The question that I want to answer in this lecture is how can we make arithmetic operation we want to perform reversible? And we're going to look at a technique that is based on scratch qubits. But what are the scratch qubits? Scratch qubits are nothing else than temporary qubits that are going to store additional data while we're doing the operation. The operation that we're going to look at is the absolute value function that will be an otherwise reversible operation unless we use the so-called scratch qubits. So let's start thinking how we can make the absolute value function on the QPU. Well, the first step will probably to negate integers in the QPU register if they are negative. We might think just to implement a very simple quantum circuit to negate or flip the sign in our QPU register depending on the sign a bit. However, no matter what, no matter how many attempts we try to do this, this operation will fail to be reversible. And the reason for that is that as soon as we apply the negation, we lose the information about the sign. So no matter how much we try, we are not going to be able to make this operation reversible because during the negation operation, we are going to lose the information about the sign. So we cannot go back to the original value we apply the absolute value function to. An easy way to make this operation reversible is to introduce a scratch qubit. In this case, we have a quantum register A, and then we introduce a scratch qubit to store the sign. What we want to do is to basically make absolute values of these quantum register values A. What we're going to do is to stash the sign of the integer in the scratch qubit. So we applied a 0 here to the scratch qubit. So we do a write operation, and then we do a control not operation on the highest weight qubit in the register A. So we have a C naught. In this case, remember here is the qubit for the sign. So if it's 1, this must be negative. So it's going to apply a not operation in this case if the negative sign here. So we're going to have a 1. And then we want to extract the absolute values of the A, and we do a conditional negation. This is the negation operation that we saw in the previous lecture when doing quantum arithmetics on the scratch qubits. So if this qubit is 1, that means that the sign is negative, then we're going to make a negative operation on the quantum register A. So we see that this scratch qubit is nothing else than couple to the register A and take the sign, stash the sign, and then use this qubit to make a conditional negation on the quantum register A. So I said that we somehow couple. So the important thing is we do not copy the sign, because at this point of the course we know that the copy operation is not allowed by quantum mechanics. Quantum computing is something that there is a non-cloning theorem that does not allow us to perform any copy operation. Instead, the C0 operation that we use between our scratch qubit and the highest qubit of the register A that tell us that the sign does not copy the sign qubit exactly because of the non-cleaning term. Instead, what the C0 does is to entangle the scratch qubit with the sign qubit. Let's look at the workings of the scratch qubit circuit that we did to implement the absolute value function in quantum computing. So we use this circular notation for the different values of the rho are the values of A. So we're having 3 qubits, and that means that we have 8 values, and then we're using negative integer, so we know that the highest qubit is for a negative number. And then we use the different values on the 2 columns for the 1 qubit, that is our scratch qubit. So if we, at the beginning of our initialization, our circular notation is the following. So we have the scratch qubit in the 0 state, so it's here. We have the values of A in arbitrary state that have been depicted on these slides here. Right. So here some circuit is missing that corresponding to prepare to this superposition of state. So let's take just as arbitrary case. Then we did a first control not operation, and the effect of this control not operation is the following. So we move the negative number, the negative quantum state integer to the second row. What happens then when we apply the sign? What we're going to do is to move it to the positive numbers of our quantum system. So we saw that if we try to perform an absolute value function without a scratch qubit, our circular notation would only have one single row, so this won't be available. So moving the negative value circles into the corresponding positive values would obliterate the magnitude and the phases. So the scratch qubit gives us this extra row that we say here. We can move into and then across in, leaving everything from the original state untouched and most importantly recoverable, so we can go back. So this is the last slide of this lecture, and talk to you soon.